Will a solid form or won't it? That's the question for today's video, predicting precipitation. A reminder that when we use the word precipitation in chemistry, we're really talking about solids. Back in first term, we learned about double replacement precipitation reactions. You take two solutions, you put them together, and out of nowhere, a solid forms. But it's not always so simple. You got to have the right concentrations to begin with in order to know if that solid is going to be made or not. We can use something called KSP and QSP to decide. You know about KSP, it's called the equilibrium constant for solubility product. QSP is essentially the same thing, but not necessarily at equilibrium. I'll show you what we mean as we wander our way through this. Let's take a look at this reaction right here. If I take a solution of potassium iodide, Ki, and I react it with a solution of PbNO32, that's lead 2 nitrate. Both of these are aqueous solutions. Put them together, and you start to see this yellow stuff. And yellow stuff is a solid. And the solid is PbI2. I know that by looking at solubility rules. The other product is KNO3. It stays in solution. It stays aqueous. The question for us is, are we guaranteed to get that solid PbI2? And the answer is no. See, here's the thing about KSP. KSP is kind of like a maximum occupancy sign you might find in a restaurant. If I say that my restaurant's allowed to have 49 people in it, and the fire marshal walks in, and there are 54 people in the restaurant, what's the fire marshal going to do? Fire marshal is going to kick those people out of my restaurant. Likewise, if I have something like PbI2, or let's say instead of focusing on the PbI2, let's focus on the ions that make it. I have Pb2 plus, and I have 2I minus. If I exceed a certain number of ions here, if I have too many ions, they get kicked out of solution and they form a solid. And we can decide that by looking at what's called the reaction quotient, QSP, and comparing it to KSP. So this is a little bit confusing for now, but just remember this before we move on. KSP is kind of like the maximum occupancy sign. If we exceed KSP, then our ions get kicked out of solution and they form a solid. If we are below KSP, then our ions can stay in solution and a solid won't form. Let's look at a problem together. Let's say I've got equal volumes of 0.01 molar barium nitrate and 0.05 molar sodium sulfate. The first thing I want to do is write a double replacement reaction. So I'm going to take barium nitrate and I am going to react it with sodium sulfate. And I get two products. One of those products is potentially a solid. It's the only thing that we really care about. Now, I know my solubility rules, but you may not remember them, and that's okay. I'm going to give you a trick for how you could come up with that information. Notice I'm not worrying about balancing this equation. It's not really important. What we want to do is find out what the solid is. So I'm going to go looking around for it. If I go back several slides all the way to here, this lists all of these solids. If I think about the two compounds that I had in the products of my reaction, only one of them is going to appear on this list. Now, I happen to know it's barium sulfate. It's right here. But if you went looking for sodium sulfate down here somewhere, it's not on here. That's because it's aqueous in solution. So let's try to remember this number, 1.1 times 10 to the minus 10. That's the KSP. And remember, we're thinking of that as a maximum occupancy of sorts. So the KSP is 1.1 times 10 to the minus 10. It's a big deal. That's for this compound right here. Now, I'm actually done with the double replacement reaction now. I found my solid. I'm good to go. What I care about now is the reversible reaction that exists between this solid and its aqueous ions. Notice I didn't say necessarily equilibrium. I'm not necessarily at equilibrium right now. So I've got Ba2 plus and I've got SO42 minus, and both of these are aqueous or aqueous. But I'm not going to put down X and X like we've done in previous problems. We're not at equilibrium. And in fact, I already know their concentrations. Let's talk about that. This says I have 0.01 molar barium nitrate. That's actually the same thing as saying 0.01 molar Ba2 plus. Secondly, I've also got 0.05 molar Na2SO4. Well, that's the same thing as saying 0.05 molar SO42 minus. Now, I would love to plug these into an equation, but I can't. And there's a reason for that. This picture below should demonstrate that. Let's pretend one is barium nitrate and one is sodium sulfate. I know that that's actually not true. Neither one has color. They're clear. But think about what molarity means. Molarity, capital M, is moles per liter. What happens when I mix these two solutions together? I pour them into one another. Maybe I have, maybe I have 100 milliliters here and 100 milliliters here. And I put them together. Now I have 200 milliliters. I doubled my volume. So just this liters right here is times 2. Well, what does that mean for my molarity? My molarity actually gets cut in half. So I may have started with 0.01 molar barium, and I may have started with 0.05 molar sulfate, but by mixing them together, the volume doubles and the concentration gets cut in half. So now I have 0.005 molar barium. I lost a 0 there for some reason, so let me draw it in. That's half of what it was. For sulfate, same thing. It's now half of what it was. For these predicting precipitation problems, it's always going to be like that because we're always going to mix equal volumes. And so our volume is always going to double and our concentration is always going to be cut in half. Let's talk about QSP. QSP equation or expression would be written just like a KSP expression, but it's just meant to be not at equilibrium. It's called the reaction quotient. And instead of plugging in X and X, I'm going to plug in my known concentrations. So I'm going to plug in here 0.005 for barium. I'm going to plug in 0.025 for sulfate. I'm going to see what the math tells me on that. If I take my calculator and I punch in 0.005 times 0.025, get a very small number. I get 1.25 times 10 to the minus 4. Let me write that down. Q equals 1.25 times 10 to the minus 4. Think about what K is. K is 1.1 times 10 to the minus 10. So clearly here, Q is bigger than K. Let's go back to our restaurant analogy. You got 54 people in my restaurant, 49 are allowed. The fire marshal walks in, sees 5 more people than are supposed to be there, so he kicks them out. Q here is bigger than it should be. I should never have that many ions in solution. And so anytime Q is greater than K, that means ions will get kicked out of solution. Another way of saying that is a solid or a precipitate will form. So again, we're predicting that solid will form in this reaction because our Q value was greater than K. Let's come back and talk for a moment before we look at one more practice problem.